All right, we'll see how far you get. I don't expect you to get through all of them in class, but we'll see. So which of the following best describes the data in the table? So we look here, we have exponential with a growth factor, linear with a rate of change. We know what those are. Quadratic with a second okay. That wasn't in our standards. You don't know that. So, and then D, none of the above. So let's see. Let's see if we can logic our way through this. Well, linear with a rate of change of 6 would mean that we're adding 6 each time. Is that what's happening? No, so it's not that. We still don't know what this quadratic with a second difference of 12 is, so let's go up to A. Exponential with a growth factor of 3. Well, that means that we would be multiplying by 3 each time. Is that what's happening? Yeah. So that's what it is. Exponential with a growth factor of 3. You'll learn what this is, probably in Algebra 2. And so clearly it's not D because it was A. You could possibly practice this with CC2 to compare linear functions with exponential functions, especially when they come from a table. 44. Since the year 2001, the population of a community A grows exponentially as illustrated in this table. The exponential rate of growth is 1.3, so each time it's being multiplied by 1.3. What are the units for the rate of growth in the table? All right, so we actually don't care about the exponential growth. What we're saying is that when it's going up, how do we talk about that? Well, we would talk about it by people per year, right? So this year it went up that many people per year. So clearly our answer is A. Nice and easy. No practice for that one. Okay, 45. Determine which of the following equations represents exponential growth or decay. I'm going to show you two different ways of working your way through this. The safer way is to make a table. Pick some values for x and look at the first equation, 0, 1, and 2, and see what happens. Does it grow or does it decay? If I have 1.5 to the power of 0, I have 1, right? 1.5 to the power of negative 1, and 1.5 to the power of negative 2. So I'm just plugging my x's in for my negative x's. And what do I get? I get, when x is 0, I get an output of 1. When x is 1, I get an output of this fraction. So that is getting smaller. That's decay. All right, equation 2. Let's figure it out again. X, 0, 1, and 2 worked last time. So my y, 0.8 to the power of 0, well, that's 1. Next one, 0.8 to the power of 1, well, that's 0.8. I'm getting smaller again, right? So there's decay. All right, equation 3. Pick the same x's. I get a y of 0.5 to the power of 0, which is 1. Now I get a y of 0.5 to the power of negative 1, which is 1 over 0.5, which equals 2. All right, so now I'm growing. Okay. And equation 4. Oops. And I can just think, oh, all right, I'm multiplying it by a number greater than 1 every time, right? So I know that that one's going to get larger, so that's growth as well. Another way to think about this is, well, what is the form of each of these equations? Y equals a times b to the power of x. Well, what is a? A is our initial value, and if we had a negative initial value, then chances are we would probably have decay, but that's not what we're dealing with here. We don't have an a in either of these. A negative b, we don't have that as a function, right? Because that puts us all over the map. So b always has to be positive non-zero. However, what if the absolute value of b is less than 1? So if this is a fraction or a decimal between 0 and 1, well, what happens is we're multiplying by a fraction every time, or rather we're dividing every time. That gives us decay. And if we have an x that's negative, we are dividing every time. So that is also decay. But what happens if we have two decays? Then we have growth. Kind of like two negatives make a positive, two decays give us growth. And so here we have growth, but here our negative x's decay, so we get decay. Here we have a fraction or decimal less than 1, but positive, and growth, so we have decay. So we have decay and growth gives us decay. And here we have decay, but also decay. And so those two kind of cancel each other out and give us growth. And then here we have growth, and that gives us growth. Confusing. I would stick with making tables. Our answer is B. CC6 maybe, but I wouldn't recommend it. 46. If f of x equals 3 times 4 to the power of x and g of x equals 3 times 2 to the power of x, compare the functions. All right, let's see. Well, first we know that we don't have x-intercepts, right? This might approach 0 in either direction, one of the two directions, but it's never going to hit 0. So we don't have an x-intercept, so we know it's not A. And let's see, let's look at our main form, right? Our standard form, our generic form, I should say. F of x equals a times b to the power of x. So what do we have here? We have the same a's, and we have different b's. Those b's are our rate of growth or decay, right? That's that repeated multiplication or repeated division. Well, in this case, one is being repeatedly multiplied by 4, and the other one's being repeatedly multiplied by 2. So, do they increase at the same rate? No, we know it can't be C. Okay, now we're looking at y-intercepts for both our last questions. Well, remember what y is? Or rather, sorry, remember what a is? A, that's our initial value. That's our y-intercept, right? Because if x is 0, that turns b to the power of 0 into 1. So that means f of 0, actually I think I did that, there we go. B to the power of 0 equals 1. So that means f of 0 equals just a. So that gives us our y-intercept. Well, they both have the same a, so they have the same y-intercept. Okay. CC3 maybe, again, IXL isn't helping us as we're getting through these. I might just stop giving you recommendations pretty soon. 47, what is the solution for x in, back to easy ones. Here we go. 4 to the power of, so we need to make our bases the same. 4 to the power of x equals 4 to the power of, what's going to give us that 64? 4 to the power of 3. If our bases are the same, we can make our exponents the same. X equals 3. There we go. 48, slightly more complicated version of 47. So let's see. 5 to the power of 2x minus 9 equals 125. We need our bases to be the same, so 5 to the power of 2x minus 9 equals 5 to the power of 3. There we go. Bases are the same, so our exponents need to be the same. 2x minus 9 equals 3. Easy algebra problem to solve. Add 9 to both sides. Divide both sides by 2. X equals 6. 49. What is the solution of the system graphed? Another easy one. Our solution, that's where they intersect, right? That's a system. Solution is the point of intersection. Our solution is 2, 4, because there it is. Go over 2, up 4, there's our point, 2, 4. There's our solution. 50. Slightly more difficult system, but not that difficult. What do we have? We have two variables that are the same. So we can use substitution, right? Or set them equal. So we would say 2 to the power of x equals 8. Oh, nice and easy, just like what we've been doing. 2 to the power of x equals 2 to the power of 3. That means x has to equal 3. So we get dx equals 3. Again, I was able to do that because I had two values of y. I had a system. I could substitute this value of y in for that value of y. 51. Which of the following represents this function? Well, the first thing we can do is we know that this function is going to be increasing. So we know that it's not going to be C or A. But let's see. Let's make a table. If we have 0 as our input, we have 2 to the power of 0, which is 1. 1 minus 5 gives us negative 4. If we have, so now we know our y-intercept. So we know it can't be these two. Hey, look at this. We knocked out this one, and this one. It's going to be this one. I kept going. I made it kind of the rough way. I said, all right, let's figure out another point. If we had 3 as our input, because look, I can see 3 here easily just to confirm. 2 to the power of 3 is going to be 8. 8 minus 5 gives us an output of 3. Does that give us that? It sure does, so our answer is B. Another way I was able to prove that our answer is B multiple ways without having to make a very big table. 52. Write a recursive formula. Oh, yay, you're so happy about this. I know, I can tell. Recursive formula for the sequence below, assuming f of 1 is the first term in the sequence. F of 1 equals, well, look, first term in the sequence is 3. Neither of these say the first term of the sequence is 3, so we can knock out A and B right away. Test-taking skills. You guys are good at this. Okay. Now we'll look at our sequence. So what's going on? This sequence is geometric. We're multiplying by a number each time. This sequence is arithmetic. We are adding or subtracting a number each time. Well, what's the pattern? What's going on in between each one? And by the way, if you're freaking out about this format, yeah, it looks a little backwards from what we did in class, but it's the same thing. Our current term equals the previous term times A. Looks the same thing. Our current term equals R. Why did I say A there? Pardon me for a second. Times R. There we go. R times the previous term. Same thing, just a different order and a different terminology. We're using A sub n instead of F of n. Same thing. All right. So in this case, we'd be multiplying by R would be -2. In the other case, we would be subtracting or adding a negative, once again, D was the common difference. Okay. So what's happening each time? Are we subtracting by a number? No. We're multiplying by -2 each time. So the answer is C. Another way to figure this out, if you wanted to, if you thought about D, I could think about, well, term 2 and compare that to term 1. And so I'm practicing with D because I would practice it for more than one. So I'm just plugging it in. F of 2, so that's the second term, equals the first term, the previous term, minus 9. Let's see, the second term is -6. The first term is 3. Minus 9. Yeah, that works. So let's test it again. Always test it more than once. The third term should equal the previous term. That would be the second term, minus 9. Let's see, so that's the third term is 12, right? Does that equal the second term is -6? -6 minus 9? No, it doesn't. So once again, it cannot be D, it has to be C. So use what you know to work through these, even if you can't remember the formulas. That's okay. P6, though, might help you compare arithmetic and geometric sequences and write their functions, write their formulas. 53, explicit formula for the geometric sequence. And if I look at this, even if I don't remember the geometric sequence, if I look at this, A sub n equals a number times another number to the power of n minus 1. Okay. So A sub n equals A sub 1, so that must be my first term, times R to the power of n minus 1. Okay. And this is an ugly one. I'm getting two values, two terms that are not consecutive, and neither one is my first term. All right. So, and it also tells me to assume the common ratio is positive. Okay. So let's plug in what we know. Let's plug in A sub 3. So we get A sub 3 equals A sub 1 times R to the power of 3 minus 1, right? Because we're looking at the third term, R to the power of 3 minus 1. So then we get A sub 3, so our third term is 1, equals A sub 1. Can't figure that out. Times R to the R squared, right? And now I'm going to continue solving. I'm going to solve for A sub 1. I'm going to solve for that first term. 1 over R squared equals A sub 1. Because all I did was divide both sides by R squared. Okay, let's do the same thing for the other term. Let's do it for term 5. So here's our initial formula. A sub n equals our initial value, a sub 1, times r, that's our common ratio, to the power of n minus 1. So a sub 5 equals a sub 1 times r to the power of 5 minus 1, right? Fifth term. A sub 5 is 0.25. I'm going to convert it to a fraction. You can leave it as a decimal. 1/4 equals a sub 1 times r to the power of 4. Divide both sides by r to the power of 4. I get 1 over 4 times r to the power of 4 equals a sub 1. What good does that do me? I have a system now, right? So let's set these two equal to each other. 1 over r squared equals 1 over 4 times r to the power of 4. Let's go ahead and cross multiply. I'll get 4 times r to the power of 4 equals r squared. Let's divide both sides by r squared. I get 4 times r squared equals 1, right? And let's keep solving for r. So I get r squared equals 1/4. I just divided both sides by 4. And let's take our square roots. R equals plus or minus the square root of 1/4. R equals plus or minus 1/2. Remember, pause and talk about it if you have to. But now what did it say? It said our common ratio is positive. So I can say our ratio is equal to 1/2. All right, so what can I do now? Well, actually, I can just say, what's the only one with a common ratio of 1/2? That's this one. But if I wanted to, I could go back into one of my equations and solve for my initial value. My a sub 1 is 1 over r squared. So a sub 1 equals 1 over 1/2 squared. So a sub 1 equals 1 over 1/4, right? Because that's 1/2 squared, which means a sub 1 equals 4. And sure enough, up here, still at b, our initial value is still 4. Okay? The key to these is to remember a sub n equals our initial value, a sub 1, times our common ratio to the power of n minus 1, which is very much like y equals our initial value a times b to the power of x. Very similar. Not the same, but very similar. Hopefully these echoes will help you remember. Okay, 54. Which of the following functions is equivalent to this function? All we need to do is solve one way or the other, right? So sometimes I'm going to start with this one and solve to see if I get that. Sometimes I'm going to start here and solve to see if I get that. So let's see, Roman numeral I, g of x equals 3 to the power of negative 2. Well, 3 to the power of negative 2, remember, is 1 over 3 squared, right? And I can rewrite that as 1 over 3 to the power of 2, because 1 squared is 1 squared. 3 squared is 3 squared. So this is equivalent. How about the next one? I started up here. 1/3 squared is equal to 1/9. There we go. We know that 2 works. How about 3? I'm going to work down here again. Well, if 2 to the power of negative 1, that's going to become the denominator. 3 to the power of negative 1, that's going to become the numerator. So that's going to be equal to 3/2. Well, that's nowhere near that, so that's not one of them. Okay, g of x equals, really? That's negative 6. That's definitely not one of them. For number 5, I just compared. Remember, I simplified to 1/9 before, so clearly that's not going to be true. And how about this one? G of x equals 9 to the power of negative 1. That's 1 over 9. I solved that one before. Remember, I said that's 1 over 3 squared. That's equal to 1/3 squared. So that works. So Roman numeral 1, 2, and 6 work. There we go. Okay, number 55. Use the table. Oh, yay, they gave us a table. To figure out which one gets larger and larger, which value of x gives us the most increase in the function. So we'll fill out the table. Pause if you need to. I guess I should say this out loud so you can compare your paper. H of x is going to give us 27, 64, 125, 216, because all I did was plug in 3 for x. And now I'm going to plug in 3 for x here. I'll get 3 to the power of 3, which is 27. 3 to the power of 4 is 81, and so forth. Well, which function has the greatest value as x gets larger and larger? Clearly it's this one, because that's huge compared to the other ones. So D is our answer. Okay, last one in this set. The maximum height reached by a bouncing ball is given by this function. So remember, there's our initial value, there's our common ratio to the power of x, where h is measured in feet and x is the bounce number. Describe the domain of the function and what it means when x equals 0. All right, so let's draw a graph. Domain. Let's think about what could possibly be input. If I'm talking about the bounces of a ball, it might go down kind of like that. Am I ever going to have negative bounces? No. Is the ball ever going to have a negative height? No. And it's definitely not going to end up ever being there. So the domain is actually all non-negative integers, right? All the inputs, we can't put in any negative numbers, but we could put in 0. We could have 0 bounces, and we could put in all these numbers until we run out of bounces. So A and B make no sense. The domain is not all real numbers. Okay, so the domain is all negative numbers, or 0, 1, 2, 3. The domain represents the bounce number x and does not have units. I actually disagree with that, because I say that the units are the number of bounces, but whatever. This is the same for both questions, so I don't even need to argue about that. Okay, when x equals 0, the height h of the ball is 10 feet, or when x equals 0, the height h of the ball is 7.5 feet. Well, I could either look here and remember that this is my initial value, or I could plug it in. H of x equals 10 times 0.75 to the power of x. So if I plug in 0 for x, I get h of 0 equals 10 times 0.5 to the power of 0, or 0.7, yeah. This is going to equal 1, right? So h of 0 equals 10. That means my initial value is 10, 0, 10. That means that my answer is, when x is 0, the height is 10 feet. My answer is C. All right. Thank you guys for fighting through this. I hope you guys were awesome with the substitute. You're probably not even hearing this, because I'm guessing you didn't even get to this problem. If you did, wow, I am beyond impressed. And I will see you guys on Thursday. Have a good day.